All right, this problem asks us to determine the small gravitational force F which the copper sphere exerts on the steel sphere. Both of the spheres are homogeneous, and we know that the value of R is 50 millimeters, and then express our result as a vector. So we have copper and steel, and if we think about the force that would be experienced, we could sketch that because copper will pull on the steel, and the force would be directed from the center of the steel back toward the center of the copper. Now I'll just leave it like that and then sketch kind of a diagonal to do the rest. But we can call this the force of the copper on the steel. Okay? Now this force is going to be at some angle, theta, and we could find theta rather easily. Theta would be the tan inverse. If we look at this triangle that is composed of a vertical side 2r divided by a horizontal side of 4r, the r's would drop. So even though we know the value of r, it doesn't matter in our equation. So we'd have the tan inverse of 2 divided by 4, and that number is 26.6 degrees. Okay. Now, as far as the equation for the force, we know that the force of the copper on the steel, using Newton's law of universal gravitation, would be big G, our gravitational constant, multiplied by the mass of the copper times the mass of the steel, divided by the distance, and I'm going to write it as d, where d is the distance between the centers of the two spheres, squared. So that distance d would start at the steel center and go back down here to r. So I'll write that as a little d. Now we need to know what the little d is, and we need the actual dimension for this, and that's not too bad. R is again 50 millimeters, so we know that this 2r dimension is 2 times 50, or 100 millimeters, and this 4r dimension is 4 times 50, or 200 millimeters. And d would just be the square root, or the hypotenuse of this triangle. So we know that d is the square root of 100 squared plus 200 squared. And that number comes out as 224 millimeters once we round it. Okay? So, big G is a constant. We can look that up in our tables in the back of the book. And since this is a metric problem, we know that G is 6.673 times 10 to the negative 11th, and the units for that are meters cubed per kilogram second squared. And we're left at this point just solving for the mass of the copper and the mass of the steel. And that is a little more involved of a calculation, but not very difficult. The mass of the copper may be found by multiplying the density. So let's just write steel. May be found by multiplying its density, we'll call that rho S, times its volume. So the density can be found in your textbook. And if you look at table D1 for physical properties, we have the densities given, again metric. So the density for the copper is given to us as 8,910 kilograms per meter cubed, and the density for the steel is given as 7,830 kilograms per meter cubed. So for the steel, we can write this as 7,830, and then the volume of the steel, this is a sphere, and the volume of a sphere, we'll just write sphere, is given as 4/3 pi r cubed. So this would be 4/3 pi. The radius for the steel, note that it is given as r over 2. And so the R over 2 means that we have a 25 millimeter diameter sphere. So we'll write this as 25 divided by 1,000 cubed. And if you carry out that math, you would find that this mass is 0.512 kilograms. We can do the same thing with the copper. Mass of the copper is rho for the copper times the volume of the copper. The density for the copper was given as 8,910 kilograms per meter cubed. And again, the density, or the volume, excuse me, is 4/3 pi times r cubed. And this one is just r, so that's easy to work with. 50 divided by 1,000 cubed. And if we carry out this math, we would find that the mass of the copper sphere is 4.67 kilograms. So a little heavier, or a little more mass, I should say. Don't want to say heavier because kilogram is mass, not weight. All right. So we have those two values. I'm just going to move them over here for the time being. And we can now compute the force that is exerted. So we just substitute. So the G, 6.673 times 10 to the minus 11th, multiplying the masses. So we have 4.67 times the 0.512, and then that is divided by the distance, which we computed earlier as 224 millimeters, 0.224 meters squared. And the value for this is very small. We wind up that the force of the copper on the steel is equal to 3.19 times 10 to the negative 9th power newtons. Now, it's important to remember everything needs to be in similar units. G has meters as its fundamental length unit. So when we went through here in this equation where we had this length, we had to make sure we used meters and not millimeters. The same thing was true in our mass calculations. The densities were given as kilograms per meter cubed. So and it's important that you put in a length dimension of meters. And that's why we divided our radii by 1,000. And just to be complete, let's go ahead and write rho for the copper, 8,910 kilograms per meter cubed. All right, at this point, we can actually finish the question because we were asked to express our result as a vector. And if we want to write that as a vector, we know the direction. It's in the minus I and the minus j directions. And we could simply write that the vector, force for the copper on the steel, is the magnitude times the unit vector that aims it. In this case, it's going to be a minus cosine theta in the I, minus sine theta in the j. So that's equal to 3.19 times 10 to the minus 9, multiplying a minus cosine of 26.6 degrees in the I, minus the sine of 26.6 degrees in the j. And as a vector, the force which the copper exerts on the steel is equal to a minus 2.85 in the I, minus 1.427 in the j, 10 to the negative 9th newtons. And that is our final answer. All right, so a little more involved problem, but let's just review what we did. We wrote our general expression for the force. G was easy. That's a constant we can get from our book. We had two masses, which we used density times volume expressions for, remembering that the volume of a sphere is 4/3 pi r cubed. So we got two masses. We had to find a distance between the two centers, so a little bit of geometry to get that distance as well as the angle so that we could aim the force. Now, if the problem had asked us for the force which the steel sphere exerts on the copper sphere, the vector would look almost identical, except it would point in the opposite direction. It would have the same magnitude, it would have the same angle, but it would point the opposite direction, so these would both be positive numbers instead. So a good question.